Hello my dear students, here today we are in lecture number 63. One topic it was left in Earth Magnetism, lecture 33, chapter 5th of NCERT, Magnetism and Matter. We'll try to finish first the topic it was left in last lecture, and it was Earth Magnetism. Okay, the topic of Earth Magnetism. The components of Earth magnetism we were discussing. Component. Without much discussion, I will start. Remember, as I told you, for describing the magnetic field of the Earth, we need to specify three components, and the first it was declination. Okay, or you can say angle of declination. Angle of declination. It is represented by D. In diagram we have drawn. It was D. Kindly go through the last lecture. Write the definition directly. It is the angle between geographic meridian and magnetic meridian planes. Okay, it is the angle between geographic meridian and magnetic meridian planes. That's it. Nothing more you have to explain in examination. Okay, now the second one. Second one is the angle of deep. Angle of deep. In this, or you can say the angle of inclination or magnetic inclination. Okay, or magnetic inclination. This is called the angle of deep. While studying this particular angle of deep or magnetic inclination, you will be able to find the horizontal component of Earth magnetic field, which is the third component of Earth magnetic field. Okay, so try to understand here. Student, the actually angle of deep we have studied in the diagram. It is the angle made by the resultant magnetic field. Okay, resultant magnetic field with horizontal, with the horizontal. Okay, remember, to study this particular thing we use an instrument, and that instrument is called deep circle. It is called deep circle. So let me draw that deep circle, then we will study in very detail about it. It is evacuated in a glass chamber. This is stand. Okay, yes. This is a vertical axis. And this is a horizontal axis. A magnet at certain angle you can consider here. A magnet, it is pivoted at this point. All right, and this particular point is painted to represent it is north. Now this direction, basically I am telling you, it is the net magnetic field of the Earth. B is what? Resultant magnetic field. Magnetic field. Okay, it is a resultant magnetic field. It makes certain angle with the, this is the horizontal and this is the vertical. It makes certain angle. This is called theta, and this theta is considered as angle of inclination or angle of deep. Angle of deep. For the name of this particular device, my dear students, I told you the deep circle. This is called deep circle. Okay, name of this device is deep circle. All right, if this is the magnetic field, then this magnetic field have the two component, one along this axis and another along this axis. Okay, its component, that is the magnetic field of this earth, has the two component, one along this axis which is the horizontal, and basically this is nothing but the equator. Remember, this is the equator, and you can say this is the pole. This is the equator and this is the pole, you can say. All right, so this will have the two component. It is measured by deep circle. The component you can write here, the horizontal one. Oh yes, horizontal component can be written as BE cos theta. BE cos theta, and the vertical component can be written as the BE sin theta. All right, if you wish to find out the value of net or the resultant magnetic field somewhere, if it is given horizontal and vertical one, then you can find the value. How? Squaring both the equation 1 and 2 and sum up h square plus v square, what you will get? BE square cos square theta plus BE square sin square theta. All right, here the BE square common, and this will be under root. Here eliminating the square, h square plus v square. I hope you understand. So this is the magnetic field, resultant magnetic field. If somewhere the horizontal and vertical component is given, then you can find out. Even the horizontal component is given, then you can find the angle of inclination, that is the angle of deep. Again, I'm telling you, this theta is the angle of deep. All right, suppose if you have to find the angle of deep and the vertical and horizontal components are given and you have to find the angle of deep, then how you will find it? Okay, so let me rub this one. We are discussing the component. So dividing these two equation 1 and 2, dividing these two equation, you can find the V by H. It is BE sin theta over BE cos theta. All right, this B will be cancelled out, and it gives you the tan theta, that is theta is tan inverse V over H. So you can find out the angle as well. Suppose if the angle of deep is given somewhere, then you will have the relation between the vertical and horizontal component of the Earth's magnetic field. Okay, my dear student. Now, what was the third component? Third component, it was horizontal component of Earth's magnetic field, that is BE. It is quite clear. The horizontal component is nothing but the H, and it is BE cos theta. Already you know about this theta. It is angle of inclination. So don't be confused between angle of inclination or the declination. Remember, the declination, it is the angle with which the magnetic dipole, that is the magnetic field, the magnetic dipole or the magnetic north and south pole, decline the geographic one with certain angle. Okay, so here the next topic, my dear students, this will start. It is the elements of magnetism. Okay, give the heading, elements of magnetism. Elements of magnetism. You will get 2 to 3 questions in examination on the basis of this particular topic, the Earth magnetism. Okay, the Earth magnetic field. Okay, the elements of magnetism. The first topic we will study the magnetic induction or magnetic flux density. Is that magnetic induction? 1. Magnetic induction. or you can say magnetic flux density. Okay, magnetic flux density will represent it is with the symbol, it is B. It is a magnetic induction. Suppose we are having an the magnetic field like this way. Okay, the magnetic field like this way. This is the magnetic field. If we place a sample inside this magnetic field, the magnetic sample, remember, the dipoles are having, when this sample is placed in this magnetic field, that is the external magnetic field, all right, the external magnetic field, it is placed, and additional field lines, you can see this additional field lines, actually there will be the dipole of this material. Okay, this is the dipole, they are oriented in the different manners. Okay, as soon as we will apply here the field, all the dipole will try to orient itself, the red one representing the final orientation. Okay, this is the final orientation of all the dipole. You can see it is all in one direction. Okay, in same direction, all are moving in same direction. It means this field lines, okay, or the field lines with the help of these dipoles will sum up with the field lines of this external magnetic field. We know that this external magnetic field can enter, and this material will allow to move through this. Okay, we will study the permeability also, the another component. But when the sample is placed in this external magnetic field, an addition of field lines induced. Okay, in addition of this magnetic field lines which is induced, which gives the induction. The magnetic field of sample, you can write, this is the magnetic field of sample. Actually what it is the sum of external magnetic field, or the field lines, you can say this is the magnetic field density, or the field lines, you can say B. What it is, the external, this one is the B external. All right, B external plus the magnetic field produced, that is the B produced due to what? B produced due to the magnetization of material. This material now magnetized. B produced due to magnetization of, let me write in proper way, magnetization of material. Okay, of material, and this is the sum of these two field lines. Okay, so the total number of lines of forces, you can say the total number of lines of forces with the specimen or the sample per unit area. This per unit area, you can say the per unit area is called magnetic induction. How many field lines it is now linked with this per unit area due to the addition of this external field lines, and this is called the magnetic induction. Remember, the magnetic induction, it is the net field. In short, you can say the magnetic induction, it is the net field of the sample. Okay, it is the net field of the sample. Now the next, remember, it is represented by B, and this B, magnetic field of sample, it is B. All right, yes. Now we'll study the next element, and it is magnetic field intensity. Okay, the second one is the magnetic field intensity. Okay, and it is represented by H. Of course, my dear students, we have applied here the external magnetic field to the sample, but remember, all the magnetic field, it is not linked with the sample. Okay, all magnetic field is not linked with the sample. So it is related to the magnetic intensity. You can say it is magnetic field intensity we are talking about. It is related to something current. Okay, we have discussed the magnetic flux density. It was related with the sample or the material, but now this magnetic field intensity, it is related with the current. You know very well, if you are having the solenoid, it is solenoid, all right, solenoid, and there is a winding of the wire. Suppose these are the much wires and the current moving I. What happened? Yes, it start making some magnetic field. Am I right? Yes. Now this solenoid, it is empty inside. Okay, it is empty inside. What will happen if you will put a magnetic material like iron, soft iron core inside the magnet? If you insert a soft iron core inside this solenoid, what will happen? This solenoid will experience this magnetic material like the iron start experiencing some magnetic field. Why? This is placed in the magnetic field of this solenoid. If the magnetic moments of this iron, because this is ferromagnetic substance, we will study later on, are aligned in different way, and this magnetic field which is in this direction, it will start aligning all the dipoles of this magnetic sample in one direction. It means this magnetic field inside the solenoid inducing a net magnetic field inside this particular sample, that is the soft iron core. All right, it means the magnetic field, you can write, my dear student, the magnetic field intensity. About the magnetic field intensity, it is the magnetic field used for magnetization. Okay, used for magnetization. All right, yes, it is the magnetic field used for magnetization of a material. Inside this particular solenoid, we have put a soft iron core, and it is used to magnetize that soft iron core. So this is the magnetic field used for magnetization of a material, okay, of you can say of certain value. Now, if I current we have given, and N is the number of turn per unit length. Okay, N is what? It is the number of turn per unit length. All right. Then if I the current, then you can write this particular H as N times I, and this one is very important. Try to remember this one. Okay, my dear students, and this H is N times I. The one topic we will study, it is the hysteresis curve. We will use these two, that is the magnetic field intensity and magnetic induction. Right now we have covered this two topic, and only that two topic we will use for the study of hysteresis curve. Okay. Okay, now the student, we will study the next element. It is the magnetic, you can say the permeability. Okay, represented. The third one, it is magnetic permeability. Okay, and it is represented by mu. It is mu, the same symbol what we have used for the coefficient of friction. Okay, actually it is the ability. Remember, it is the ability. You can write all the my words, remember students, that are very important. Actually it is the ability of a material to allow the passage of magnetic line of forces. Suppose this is a magnetic substance, okay, and we put here the external field. If this is the substance, we put here the external field, and this allow only the 5 field lines to cross through it. Okay, and another magnetic substance, it allow 50 magnetic field lines, okay, to allow through it. Then you can say the number of magnetic field lines allowed by both the substance, it is different. So it is the ability of any material, okay, to allow the passage of magnetic lines of forces through it. This is nothing more. Okay, it represents the degree, actually you can say it represents the degree or existence to which a magnetic field can, all right, permeate. It can permeate, okay, to the material. Now, my dear students, you can say the term magnetic permeability actually deals the degree of concentration of lines of force in any particular sample, okay. And this magnetic permeability, it is defined as the, mathematically you can write, it is defined as the, that is mu, it is defined as the number of lines of force passing per unit area, okay. It is passing per unit area, and mathematically you can write as the ratio of magnetic induction. It was magnetic induction, it was represented by B, magnetic induction, to the magnetic intensity, that is the H, okay. This will be the formula of magnetic permeability. It is mu is equals to B by H. All right, you can write his SI unit also. SI unit you can write Tesla meter per ampere, all right, or you can write the Weber per meter per ampere, or Weber per meter per ampere. This is the SI unit. What is this B? This is the magnetic induction. What is this H? It is the magnetic intensity. I hope you remember. Now, my dear students, simply you can get the relation between these two, that is the between B and H. You got the relation. B can be written as the mu H. This B you can write, it is mu times H. You will use this equation later on, okay. Now, my dear students, relative permeability. So the relative permeability, the next one, next element you will give the number, it is the relative permeability, represented the mu R, all right. And this relative permeability of a material define the ratio of the number of line of magnetic induction per unit area, that is the flux density, simply you can say, all right. And in any material, the number of magnetic line per unit area that would be present if medium were replaced by a vacuum, then we can write, my dear students, relative permeability like this way: mu R, it is B by B naught. It is the induction in proper medium and induction in vacuum. Relative magnetic permeability of a material may also be defined as the ratio of magnetic permeability, remember, of material and the magnetic permeability of free space. It means mu R, we can also write it is mu for the material and mu naught for the free space. It means mu, it is nothing but the mu R times mu naught. All right, this equation you can write. All the equations are very, very important. Now, intensity of magnetization, or magnetization you can say simply. The next topic, it is the intensity of magnetization. I think this one is signing so much. Intensity of magnetization, or simply you can say this is at the magnetization. Okay, my dear students, we will represent it is by I, and this is a vector quantity. Remember, in a particular manner we use to magnetize a particular sample. If you will place a magnetic material in uniform magnetic field, okay, when a ferromagnetic material, you can say, placed in a magnetic field, it acquire a magnetic dipole moment in the direction, okay, in the direction actually we use to apply the magnetic field. And this dipole moment per unit volume of the substance is known as the, you can say, magnetic intensity of magnetization. This I equals to M by V. Alright. So you can say the magnetic dipole moment. I hope you remember this M was M into 12, pole strength into 12. So the magnetic dipole moment per unit volume of the substance is known as the intensity of magnetization. Okay, my dear student. Suppose if you're having a sample and the length it is given, so this I can be also written as M into 12. Alright, if you're having a sample like this way, the 12 in the length, cross-section area is A, then M into 12 the M, and B is what? A into 12, that is the cross-section area into. So this I can be also written the M by A, that is pole strength per unit area. It is the intensity of magnetization, pole strength per unit area. So ampere per meter will be the SI unit. Ampere per meter, you can write the SI unit of this intensity of magnetization. Okay, my dear student. Now the next topic will be magnetic susceptibility. Okay, so we'll give the heading magnetic susceptibility. Magnetic susceptibility, it is represented by Xi M. Remember, it is magnetic susceptibility. Actually, the magnetic susceptibility is defined as the ratio of intensity of magnetization and the magnetic intensity of magnetizing field. Alright, the term magnetic susceptibility, my dear students, actually of substance refer to the ability of the substance to acquire magnetization. If you place a magnetic material in a magnetic field, then it start acquiring magnetization. And that magnetization, how much it can acquire that magnetization, it is depend upon the property of any substance, and that property it is called the magnetic susceptibility, okay, of that particular specimen. Actually, this also determine how easily this specimen can be magnetized. If it is very difficult, then the value of it will be the opposite. All right. Experimentally, my dear students, it has been observed. All right. Experimentally, it has been observed that the intensity of magnetization is proportional to the strength of the magnetizing field. It means I, intensity of magnetization, it is directly proportional to the H. What this H, actually this H was N times I, try to recall, and then this I will be equals a constant, and this constant it is called the susceptibility. Alright, this is I equals to Xi H, which is magnetic susceptibility, and this magnetic susceptibility X in the magnetic susceptibility. For given values, you can find out. Actually, the magnetic susceptibility, you can write, my dear students, in your notes. I'm telling you, the magnetic susceptibility is the intensity of magnetization developed in the substance when it is placed in a magnetic field of unit strength. All right. I hope you got it. Only measure how much magnetic field will be acquired by any substance. Now, my dear students, you can here derive a relation which might be useful for making some numerical questions. So give the heading relation between relative permeability and you can say magnetic susceptibility. Yes, relation between relative permeability and magnetic susceptibility. We are going to find out here the relation. when a substance will be placed in magnetizing field, it becomes magnetic. It will be magnetized also, all right, like a magnetic substance. The total magnetic flux density within the substance, what will be it will be the flux density. Okay, it will be the flux density that would have been produced by the magnetizing field in vacuum, plus the flux density due to the magnetization of the substance. It means the net magnetic field, you can write here, suppose my dear student, if it is a sample, the solenoid, okay, solenoid, and we put a magnetic substance inside this solenoid. If we put a magnetic substance like soft iron, what will happen? Then here, all right, what will happen? This will start magnetizing. Okay, it will start magnetizing, and the net magnetic field, we can write here, the B is equals to B naught plus magnetizing field. It is the magnetizing field. Okay, my dear students, what is the B naught? Actually, B naught, it is mu naught H, the one relation we have obtained in the last topic. And what is this Bm? So the Bm, it will be the mu naught I, this one also we have been written. So all together, and what is this I? You know that this is not the current. Actually, this is the intensity of magnetization induced in the specimen. So we can write here the B, this B, okay, it is mu naught H plus mu naught I. Now this mu naught is constant, so H plus H plus I. Okay, now you can guess what should be the next step. If you replace this I, what we got, the xi m, xi h, then we can write here the B, it is equals to, B is equals to mu naught H plus xi m into H. Am I right? Yes. Now this H can be taken as constant, and then this B will be equals to the mu naught H1 plus xi m. Yes, am I right? Now you can see this mu naught H, this 1 plus xi m, and the ratio, this, or you can write this B as the mu times H. Could you write this one as the mu times H? Yes, mu times H will be cancel out. H will be cancel out. So finally we will have a relation. This is not very difficult, my dear students. This will be cancel out H. So mu equals to mu naught 1 plus xi m, or the mu by mu naught, and this is mu r, nothing we have written, it is 1 plus xi m. So this is the relation. This is the relative permeability, and this is the magnetic susceptibility. So this is the relation. Here, my dear students, we have covered with the earth magnetism and its element. From next lecture, we will start the classification of magnetic material. Okay. Here, of course, it is signing, but I hope that you got it is the B. All right. So the classification of magnetic material, we will start from the next lecture. This is all about the today's lecture, my dear students. Thank you very much.